Today, I'm going to talk about sort of this overlooked effect that so far we've been ignored in the radio SETI. And this is something that I was very fortunate to work on because of this grant that I received as a part of the STRIDE program with the SETI Institute. And we have a paper just recently accepted, and there's a press release coming out later this week. I like to also give credit to large amount to our research assistant, Grace Brown, who carried out a large amount of work that I'm going to talk about today. All right, so let's jump on to very briefly. I guess I don't need to introduce to this audience, but still, to build up the case, what do we do in SETI? Obviously, I'm a big proponent of moving away from narrowband SETI, but for this talk, I'll probably focus. I mean, I'm going to focus mostly on narrowband SETI stuff. But I certainly agree that what Mike was saying in the morning, that time is right now to move away from narrowband SETI and start looking into like other ways by which we should do radio SETI. So, what do we exactly do in SETI? When you say we have basically carried out technosignature observations towards a given target, what do we mean? In 99% of the cases, this is what we did. We basically look for these signals, and these are like extremely narrow in frequency, unlikely for nature to produce, except few cases. I think Abel Mendez gave a very nice kind of cases where certain natural phenomena can also produce them. Those are obviously very exciting. Narrowband signals are also not stationary, they drift because of the Doppler motion. And starting from 1960 to all the way to this year, you will find like hundreds of papers on this particular way of searching. But there is one, there is a very good reason for that as well. Like narrowband signals are kind of known to be less impacted by the interstellar medium. They can pass through it without getting absorbed. And you can basically detect them across all the way to the other end of the galaxy if they're bright enough. So that's a good kind of way by which you can broadcast information or basically broadcast a powerful beacon across a large amount of sort of large distances. But obviously, there is a problem. There is a great silence. We've been searching for these signals for the last 60 years or so. Nothing come out so far. So what's going on? People have obviously given, we don't know exactly, right, like what ETI might be doing. So that's obviously the one reason. But like, is this something in terms of like narrowband SETI we are doing? Are we doing everything correctly? Or is it something that we need to adjust moving forward? So my talk today is going to focus on this one particular phenomena called scintillation. I'm sure all of you are familiar with it. If you ever looked at the bottom of the pool, you will see we've seen this pattern that it's all because of the scintillation. And that's also the reason of the atmospheric scintillation. You see stars, twinkle. So this is the phenomena that we kind of somewhat understand what interstellar medium does to a narrowband signal, and that's thanks to some of the phenomenal work done over the years. Joe Lazio, who is I think in the audience right now, and some of his colleagues have basically written this very nice paper on what scintillation might do for narrowband SETI. In fact, they argue that scintillation is a good thing because sometimes it can enhance the signal by several orders of magnitude. But all of these previous studies, and there were also a couple of papers that have come out later as well, but all of these studies basically focused on scintillation due to the interstellar medium. Nobody has so far, as far as what I've been able to collect, if I'm missing something, please point me to a reference, that nobody has so far talked about the interplanetary medium of the exoplanet system that we might be targeting. And this is a very important point, as I will kind of illustrate in the rest of my talk, that there are effects that the interplanetary medium of the target system that are so critical that they actually they are more important than the interstellar medium to some extent. So what do I mean by that? So IPM is, as we know, is the interplanetary medium. Exo-IPM is what we call the kind of a space weather, but for the other system, like exoplanetary space weather in some sense. And my entire focus of the talk is how this space weather impacts any kind of passing narrowband signal through it. So start with, what do stars do? Stars have winds these winds kind of moves across the interplanetary medium. They move with quite high velocity, and this wind is also very clumpy. It has turbulence in it. And what does that turbulence do? So if you have a narrowband signal that is going through the turbulence, what the turbulence introduces is phase perturbation. In Fourier domain, the phase perturbation means spectral broadening. And this animation kind of illustrates that. As you can see, there is a signal going from bottom as it encounters the clumpy, turbulent region of the interplanetary medium. It basically gets phase modulated, and that causes the narrowband delta-like signal to get spectrally broadened. Now, you may ask how much this spectral broadening is there? Like, is it something we can detect? And the answer is yes, it is quite significant. So in our current paper, we basically we derive a mathematical relationship of various different properties of the star itself related to the expected spectral broadening. So this is the mathematical sort of relation of like, so one of the term here, which I'm going to talk a little bit more toward the rest of the talk, is the speed of the wind, and especially the perpendicular velocity. As you can imagine, if your line of sight is this way, whatever is the perpendicular velocity of the wind is going to be more critical. Nu is the frequency of your observation, and the term inside the bracket is actually called the strength of the turbulence. And it is given by the ratio of these two quantities. I know adding equations in the talk will probably reduce sort of people's attention, but please please try to follow. This is only 2 or 3 equations that I'm going to talk for the rest of my talk, and they're critical. That's why I'm kind of explaining them here. So the strength of the turbulence is the ratio between the density perturbation and the length scale of the turbulence. Overall, if I want to put these in a very simple word, what that equation in the top actually means is that higher wind speed, lower observing frequencies, and high density fluctuation give rise to higher spectral broadening, as you can see from that equation. Uh, so is this something that I'm just kind of deriving mathematically? Is this actually been observed? The answer is yes. This has been observed quite frequently by the solar system probes. So we have launched a large number of probes to explore our solar system. And most of these probes, how do they communicate back to us? They communicate back to us using a carrier wave. So they all carry a narrowband signal on board, and they transmit this narrowband signal towards the Earth. And people actually have seen the effect of the star or our sun itself on these narrowband signal. So this is an example of I think this is the Mariner probe in 1969, when Goldstein published this very nice illustration that as the Mariner probe basically went in the solar conjecture, the signal, as you can see from bottom to the top, became spectrally broadened, and then it started becoming normal as the kind of the line of sight moved away from the star or away from the sun. So this is not something that we are kind of just saying based on our some for simple math. It is actually an observed phenomenon. We actually also understand how the turbulence actually scales as a function of distance from the star. And if you put that, you can actually get a radial dependence of the spectral broadening. So what I'm showing you here on the left-hand panel, this is like your exoplanet. And imagine that there is a narrowband signal going through near the star. The R is basically the impact distance. And as you can see, it's a very strong function of R. So as the R goes closer to the star, the spectral broadening is higher. As R is further away, the spectral broadening will be less. So you have a sort of some proportionality constant. So what we did is that in order to resolve the proportionality constant, we actually did something that I don't think so there is any other studies. We collected all the spacecraft publication where people have reported spectral broadening from the sun at various different stellar distances. So we looked through papers from 1967 to all the way to 2023, so 2013. And most of these things have reported spectral broadening at various different stellar distances. So we collectively put them all into one graph, and we got this very beautiful relationship. And phenomenally, that relationship also that we mathematically derive match exactly with the slope that we that you will find from observation. So these are like empirical evidence by which we can actually say that this is how spectral broadening changes as a function of stellar distance. Uh, Again, there is an equation at the bottom. It's quite complicated looking, but let me explain very simply what it means. You have spectral broadening as a function of the radial distance, the impact distance that I mentioned earlier. And then you also have a function of frequency, but we obviously scaled everything to the sun because this is the measurement from the sun. For different stars, it might be different. So we kind of scaled everything to the sun, and you get this nice relationship. There is a parameter called beta anisotropy, which I'll come to that in a minute. So just keep that in mind for now. So what does this thing do exactly? Like what exactly this effect will tell you? I mean, we talked about some of the tools. I think in earlier talk, we talked about TurboSETI or some of the other tools, as your favorite tool, whichever tool you have used to search for narrowband signal. It basically, it's looking for signal like this. Signal which is like perfectly narrow, delta-like signal, drifting in frequency and time plane. That's what you're looking for. But in reality, it's not so. What we kind of proved right now, even at 10 hertz of spectral broadening can reduce the intensity of the signal by a huge degree. So like it reduces by at least up to 6% of the original signal intensity by 10 hertz. So remember, this is actually not a Gaussian kind of a broadening where the signal, or even like a square broadening, where signals power get distributed equally across the channel. It's actually a Lorentzian distribution. So it will have very, very long tails. So your peak intensity that any signal search algorithm is designed to search will completely fail, will not be able to detect signals. There is some more complexity, which I don't think so people have considered, is the coronal mass ejection. So what do they do? They add more anisotropy. So remember that beta ni that I mentioned in that equation, that comes from these anisotropy due to CME. Now they are not always there, as you can imagine, right? They are just chance encounters. They can sometimes be there, sometimes they are not there. But when they are there, they they wreak havoc in narrowband signals. It basically completely destroys any narrowband signal passing through it. In fact, so we did a very good modeling, and this is some work that done by Grace here. So what we did is that we basically took different parameters of the CME ejection, like different places from the star surface, different angles, different velocities, and everything combined together. And we calculated the chance encounter. And I come to that towards the end, that what exactly we found. But we did consider the effect of the CMEs as well on the spectral broadening. Now, this was all about the sun. Not every star in the sky is sun-like star. 75% of the stars are M-dwarf stars. So this effect needs to be also considered for M-dwarf stars, right? Um, they also have a pretty long lifespan. And I think Jill is in the audience, and Jill has also advocated for searching for M-dwarf stars because M-dwarf stars have a long lifetime and they are more sort of suitable places for advanced civilization or advanced life to exist. Planets orbiting M-dwarf star are much closer to their host star. Their habitable zones are kind of more closer. As you can see in the bottom image, the TRAPPIST-1 system sits very close to their star compared to the solar system. This, again, creates more problem, what I was talking about. So what do we do with the M-dwarf star? Now, there are no obvious probe that have gone behind the M-dwarf star where we can have the empirical measurement. So we have to rely on some indirect measurements. So we kind of looked at literature about everything that we can find about M-dwarf stars, like wind. What are the measurement of wind that we have found, or what people have kind of suggested? And that varies a lot. There are some stars where people have reported very high winds, some stars where they have reported lower values as well. There are some modelings on the sort of the MHD simulations, which talks about the turbulence around the M-dwarf star. So we use all of that, and we basically incorporated the same factor as we had for the sun, but now for the M-dwarf. And I'll skip that in a minute. And we basically conducted a simulated technosignature survey. And in a simulated technosignature survey, we basically assume like we are observing a million star. Obviously, 75% of these stars are going to be M-dwarf, right? And we assume different kinds of orbital parameters and different places where the planet can exist, right? Like planets is not going to be, when we look at a system, the planet could be anywhere in this in around the star. And as you can easily imagine, if the planet is behind the star, the expected spectral broadening is going to be way, way higher. So we kind of assume various different parameters for orbit as well, different type of eccentricities, different argument of periastron, inclination angle, combining everything, and all of these things kind of put together. So this is just a table of all of the different parameters that you can imagine for different orbital configuration, and we built this histogram of expected spectral broadening out of this million system that you can observe. So what I'm going to show you here, there are two y-axis. Obviously, this is the histogram, but the y-axis, the main y-axis, is showing the survival function, which is 1 minus the CDF, and then on the y on the other side is the raw counts. So this is what you get. You can see 1 hertz. That is where typically is the assumption goes that most of the signals are like a hertz wide. But as the histogram suggests, it peaks more or less beyond 1 hertz. And the survival function, actually, as you can see, what it is suggesting is that 60% of the, or wherever it kind of encounters a certain value, you can say that every system, or like 80% of the system, will have spectral broadening more than a hertz. And 30% or 40% of the system will have spectral broadening more than 10 hertz. If you go to lower frequency, this effect is even more bad, is worse, because there is a nu to the power -4 relation, as if you recall. So what is in the last 2 or 3 slides, what I'm going to show, what is the implication of this? Like, I mean, this is a completely overlooked phenomena in narrowband SETI over the last so many years, or maybe if it has been considered, but so far it has not been like considered to the level that we can use that for prediction. If we knew about it, we could have used it before. For example, when we made the detection of like BLC1, we kind of went ahead and try and look for various different ways by which we can eliminate possible origin of the signal. But we never really considered that, is this possible for the signal to even produce in the proximity of the Proxima Cent-B, or it is completely impossible? So we are doing that in our next paper. So what we are doing is that if you have the Proxima Cent-B around the Proxima Cent, if it's going around the star, the expected spectral broadening, it's at minimum is 100 hertz, and maximum it can go to tens of thousands of hertz. So in reality, what you should have expected to find if the signal was truly coming from Proxima Cent-B, it would not look like what you see here. So by the way, let me explain what you're seeing here. This is the original detection of BLC1. Frequency is on the y-axis, and time is on the x-axis. And you will see a narrowband signal going through here. It's present for during the time when you observe the Proxima Cent. It disappears, and it again comes back when you observe the Proxima Cent. And that's also a very interesting signal we discovered. But what I'm suggesting is that in reality, if it was truly coming from that planet, it would be much, much more spectrally broadened. Similarly, there are other systems that people have targeted as well. For example, TRAPPIST-1. TRAPPIST-1 as well, same problem. You will have a spectral broadening of the order of hundreds of hertz. But this has not been considered because obviously this is an overlooked phenomenon. Yeah, so with that, I think I will just finish my talk, and maybe I'll leave the summary slide up here for any question. Before I summarize, let me also highlight some of the caveats. Like, what does this result actually mean? So I already explained that we obviously have no direct measurement of like winds or turbulence around M-dwarf stars. So we basically extrapolated the sun to M-dwarf, which may or may not be accurate. And your guess is as good as mine, and may be off by an order of magnitude. We also assume the CME injection in its environment to be symmetrically distributed around the star, but it may not be. It could be more in the elliptical plane or more towards the coronal holes or somewhere. We don't know. We also assume the habitable zone, the transmitter is inside the habitable zone. Now, it could be possible that the transmitter is very, very far away from the star. Obviously, this is all assuming like a planet orbiting a star in a habitable zone. But if the planet where the transmitter is located is much, much further out from the star, then the effects are not going to be so prominent. But something else is also that we haven't considered is that a large fraction of the stars have binary companions, which can complicate things further. Like binary stars have their own, they both stars will have their own stellar environment, and then they have an envelope of the wind coming from both the stars together, which will complicate the spectral broadening calculations further. I think with that, just summarize it that ExoIPM is an important contributor to the transmission of narrowband signal originating from a planet around any star, which has so far been overlooked. And these effects are most prominent at a gigahertz and less than gigahertz frequency. If you observe at high frequency, these effects are not so prominent, obviously. But most of the SETI, as you know, has been done mostly at 1.4 gigahertz. So this is a very critical aspect that we have to consider. CME act as an extra bump. What we found, I didn't get time to kind of touch upon that, but in this histogram, the yellow color represents the number of systems that have encountered CMEs. So you can see that CME encounter increases the spectral broadening by, I don't know, like a million hertz or so, which is like impossible. Like it just reduces everything completely and just washes away. So it doesn't even make sense. But the factor, but the chance alignment, what we were able to calculate based on all the different randomness of like opening angle and speed and how long it lasts and the origin of the CME and all that combined together, we found it's less than 4%. So we are pretty safe that only 4% of the system we are likely to encounter CMEs, but otherwise it is safe. So I think I'm over time a little bit, but I thank you for your attention.
All right, thank you, Vishal. Nature does what it will do, and very, very interesting work. And all right, well, we will move on to question and answer time. We have plenty of time. So there's a question from Nick Siegler, first for Vishal. Are you suggesting SETI astronomers revisit all their data looking for broadened signals? So maybe we've already been contacted and filtered out the data.
That is certainly possible. We in our second paper, we are at least adjusting the limits that we have placed on our. If you in SETI, what we've been doing is we putting this limit called transmitter rate versus EIRP. So when we search for n number of stars, we say that we didn't find any signals. So we say, okay, we searched 1,000 stars, we didn't find anything. That means there should be less than 1,000 stars transmitting certain level of signal. But nobody considered that maybe 30% of those systems might have spectrally broadened and that you kind of completely missed them. So we are at least doing that part, that all the previous SETI searches that people have done over the last 60 years or so needs to adjust for the effect of the IPM. They need to readjust their sensitivity limit, considering that ExoIPM is there. Now, if there are indeed a signal out there that is spectrally broadened to a certain extent, that's completely possible. We need to examine or re-examine the signal or data set that we have kind of already investigated. So this is something we are also kind of currently already undertaking, at least as part of the Breakthrough Listen program, that we are developing code and tools that allows us to search for signal that it can get spectrally broadened.
Okay. Question from Kenneth Houston. Vishal, how would you modify the NB search algorithms? Would you detect at multiple resolutions?
NB search, you mean when we are...
I'm not sure. Yeah, go ahead.
I mean, yes, you will detect if you look at the width of the signal, let's say if it is 10 hertz, and when you're searching for a narrowband signal, NB, I guess, means narrowband, I would say. So when you're searching for these narrowband signal with different widths, you will see maximum signal to noise ratio recovered where you match the basically the width of the signal, right? So if you're doing a trial run, we don't know what exactly is the spectrally broadened signal width is. So you're doing a trial run. We do that, by the way, regularly in FRB searches and pulsar searches because we don't know what is the width of the signals are. So when we look for FRBs, we basically run a window of different width, and whichever window gives the perfect signal to noise ratio match, it gives us the highest signal to noise ratio. And the same methods has to be applied here as well.
Thank you. And Eric Corpelleth comments, SETI at home has different limits out to 1.2 gigahertz, like 1.2
Yes,
kilohertz bandwidth. Yeah.
we have highlighted that in our paper, Eric. Be, be sure about that. Yes, and I kind of like that SETI at home was kind of mindful of that signal doesn't necessarily need to be extremely narrow, and they have also considered signals that are kind of spectrally broadened. So yes, SETI at home certainly did a good job at that.
All right. If a distant eddy wanted to send a signal but was aware of spectral broadening, are there any
Mhm.
countermeasures they could take to improve a transmitted signal's visibility? I guess one you
Yeah,
mentioned that was interesting, put it on the outside of your solar system on the outskirts. But yeah.
yeah, or you can transmit it on the kind of the direction that is away from the star, from your own star. That allows you to at least have slightly lower degree of spectral broadening. But like obviously, if you are closer to the star, you are basically embedded in the environment itself. So you there will be like some minimum effect, even if you're broadcast away from the star. You are going to kind of introduce spectral broadening in those cases as well. Uh, so I would say it's in fact a good thing. Like if you in fact transmit a signal um, from your planet, as you let's say you're targeting a certain system, you transmit during the time when you're transiting your own star, right? When so in that case, the signal that you are transmitting will get spectrally broadened, and that allows the receiver to verify the signal that you are actually detecting is indeed coming from a planet, because now you have a way of by which you can say that okay, there is a planet, and the planet is kind of moving behind the star, and that's why I'm seeing the effect of getting spectral signal getting spectrally broadened. I mean, if you do see that, that's like a sure sign that signal is indeed coming from a planet. There is no other way by which we can produce that effect. So, in fact, it can be used.
All right, Abel Mendez, isn't Radio SETI also searching for broader band signals using pipelines designed to detect ensembles of channels rather than strictly narrowband features?
Yes, absolutely. So in 2021, I wrote a paper in which we highlighted this pipeline called SunDuck. And in SunDuck, we actually designed an algorithm to search for artificially dispersed pulses, a broadband signal that spans the entire band of your observation. So yes, we do search for broadband signals.
All right, and then Joe Lazio, do you have any thoughts about how to better constrain M-dwarf winds?
Yeah, that's a good question. I mean, there are studies that people are doing. For example, there was this paper by Vida et al. And others. It's mostly coming from indirect evidence. Like what the wind does is that it ionizes the medium around it. So, and there are some HST observations as well. People have looked at like H alpha, Lyman alpha lines around the star, and that might give insight on like what is the amount of like m dot, as a mass loss rate of the star, and that can give you some idea about the wind. What we are kind of more concerned about is not the wind speed so much at the interstellar space or at the astrosphere limit. It's more towards the inner part where the planet is located. That region is much harder to constrain. I mean, if you want to do like some kind of VLBI observation, I mean, I've considered that, Joe. By the way, I mean, the chance encounter of having like a point source behind a foreground M-dwarf star is very low. If we can find a good source, I think that would be a good observation to do a VLBI observation. And you can basically observe angular broadening, because whatever causes the spectral broadening, same thing also causes angular broadening. So it will make a point source to get slightly more broader. It is possible, but the chance encounter is going to be very, very low.
I see Nick Siegler has his hand up. Nick, you typed it in as well. All right, well, I'll read Nick's question since he had his hand up. So, this is very good work as usual. The effect seems like a big deal. It has a potential impact on every radio SETI pipeline. Do you feel this requires community review and consensus before pipeline modifications are conducted?
I mean, I don't know what is mean by community review. I mean, paper is being kind of refereed, and it is published. If there are effects that we have ignored or we have kind of overestimated certain things, we're happy to kind of listen to that as well. Pipeline modification is going to be very subjective because we do have our own pipeline that we work with Breakthrough Listen, but there are other now Technosignature is no longer sort of done by these people in California. There are Technosignature activities going around all across the world, and there are a lot of other algorithms that people have written. So I assume everybody needs to be aware that there is this effect, and they all need to adjust their algorithms such that you don't miss a spectrally broadened signal if you do encounter them. One of the good effects is that these signals are not going to be just spectrally broadened in the sense that you will have energy distributed equally. You will have a Lorentzian profile, which is very easy to identify. So maybe one can design an algorithm pipeline that is specifically designed to search for Lorentzian kind of signal. Even like as I showed in my talk, 80% of the system will have at least 1 hertz of spectral broadening, right? And that is at the level of like Lorentzian profile of 1 hertz. So even that, considering that kind of signal detection would be a huge step.
Okay, great. All right, we'll go to Eric and then we'll move down the list. So can we presume that this would also restrict data transmission rates similarly, and that anyone wishing to transmit data would need to account for this by moving away from the star to higher frequency?
Yeah, so so Eric, I actually haven't done that calculation about like how a signal with information will get impacted by the scintillation. Obviously there will be the same effect as phase modulation, right? Because if your signal is phase modulated, let's say, and the IPM is introducing its own phase modulation, then yes, this is going to be a critical thing that you would like to avoid. Because if your signal is already having information in it, it's going to get destroyed when it passes through the IPM. So yeah, it is probably preferred for information-bearing signal to also be broadcasted away from the star.
And Jill Tarter asks, how close are we to being able to do these calculations in real time?
So in real time is not that kind of difficult. I'm working on a code in which we are putting out an online tool where you can select an exoplanet and you can select a time window. And given that time window, it will tell you that this is the expected spectral broadening for these planets. Obviously, this is all based on the information we have, like whatever the exoplanet that we have detected through transit method or to any other method, we can say something about what is the expected spectral broadening. Now, whether to do this in real-time signal searches, it is also not that difficult. It is not a huge computation burden to add an extra step in which you are searching not just one width, but across multiple widths. So although it is currently implemented as part of an offline processing, it is not currently part of our online or real-time searches, but this obviously will be updated in our real-time signal search pipelines as well.
All right. Ben Zuckerman asks, wind mass loss rates can be estimated by studying close white dwarf, red dwarf binary systems. The rate can be derived by measuring how much material from the main sequence star wind in the photosphere of the white dwarf. I guess it's a comment.
Yeah.
Nick, you have your hand up. We can unmute you if you still had something to say. Okay, hands down. That's fine. Okay, well, this was a great discussion, great session. I think our other speaker, Zhao Hang, has left, but I think she did answer the one question that was directed at her. Any other questions or comments, or Vishal, any parting thoughts? Very interesting work and definitely big implications for the field.
Yes. Thank you. Just a parting thought, as I mentioned to Jill's question, there will be a couple of more papers coming out in the next couple of months as well as a follow-up of the study. Number one is we have to revisit all the limits that we have placed on technosignature work. We are looking at our search strategies and search algorithms, how those algorithms might miss a signal like this. And second thing is that can we use this as a tool by which you can predict it? So that's also something that we are working very closely.
I see we do have a question. Edwin Turner just typed in. A classic radio SETI calculation accompanying iconic diagram indicates the ideal wavelength range to be 20 centimeters. Does this effect change that conclusion?
Well, so historically, this is what people have assumed that when you want to do like radio SETI, you try and look for hydrogen line, which is 21 centimeter. But over the years, this has expanded. If you look at the previous or past SETI effort, people have focused on very few megahertz or like even a kilohertz around like a 1420 megahertz range, right? Because it was limited in terms of what computing capacity, what hardware, or what digital instrument were available to us at the time. But now we do have a flexibility of that. We can ingest a high amount of data array. So nowadays, modern SETI searches, if you look at it, we search across like a gigahertz or more than like a several gigahertz of frequency simultaneously. So we look for like across several gigahertz of frequency, the same kind of signal.
No, that's one of the interesting things that, if you've noticed, we've been trying to feature some of the papers from the IAUS404 in 1984. And that's a big thing that changed, was the ability to search many frequencies versus a very, very actual narrow band search for what's the best magic frequency. So that's a big part of the conversation, I think, that's changed in the decades. So Jill asked how many of these strategies are being built into the SKA.
I mean, SK is sort of like it's still an open-ended question. I think I think I saw Shanoa on the call here as well. She's working very closely with the SK team, and she's leading a Technosignature paper on the SK side. We do kind of have to worry quite sort of seriously about SK low, especially because when you go to these low frequencies, as I mentioned in my talk, these effects are some of the most prominent effect that you will probably have to worry about. So I don't think so that there is even a need to design a spectrometer that of the resolution of like 1 hertz, because or even if you design it, you don't expect to find signal of 1 hertz, because 80 or 90% of the signals are going to get spectrally broadened to more than 10 hertz if you observe at SK low frequencies. As far as the implementation side of things, I don't think so there are any concrete talks yet. This is still the discussions are still in a very early phase as far as I know.
Right. Any other questions? I see no more questions. One more question. Great. Kenneth Houston, I think the classic modulation for these spread channels would be frequency modulation. Would we expect a bimodal spectrum? ET had a similar idea.
I think that.
Yeah.
Modulation signals are obviously very interesting. We haven't been searching for it. In my next proposal to Stripe, this is something that I kind of pitched in, that we need to search, and I think what Mike Garrett also said in the morning, right? We have to move away from the standard narrowband SETI we've been doing for the last so many years. It was not historically possible to do because it requires a huge amount of compute resources. You need to do this in real time. You need to have access to raw baseband voltages if you want to look for, let's say, like phase modulation. Because you look at like total intensity, where you basically throw out all the information about phase. So many things are kind of possible to do with the raw voltages. So we do have now capacity to handle large volume of data in real time, and that helps us basically search for these different classes of modulation. So my next kind of Stripe proposal is in fact designing tools to search for different classes of modulation, including the signals with FM as well. So in fact, there are like 50 or 60 different classes of modulation that people currently use for communication, and it should be possible to kind of search for all of them. Or even an unknown class of modulation. Obviously, like FM is a very anthropocentric way of saying that this is modulation we have designed, so that has to be the best way by which ETI might also communicate, but that's not necessarily need to be true. One thing we need to understand is that when we talk about beacons, we can always take an assumption that signal needs to be simple, and that's why we go for narrowband signal. But when we talk about like information-bearing signal or some kind of like a leakage radiation, a lot of papers have talked about leakage radiation, right? Like Mike Garrett in the morning talked about like Miro Saeed's work, where signals that we leaked out from all our mobile phone towers, like those are not narrowband signal, those are spread spectrum signal. So you need to be able to sensitive to detect leakage radiation, which are not going to be narrowband signal. And that's why you do need to kind of search for unknown classes of modulation that you don't really, they're not meant for us. They just leaked out by the activity, by ETI's own activity.
And Jill says, don't say move away, say do more.
Absolutely. No, I think so I'm not saying that narrowband SETI should be completely avoided. That's the lowest hanging fruit. We need to keep doing that, but we also need to expand to do other things as well. Yes.
Abel, yeah, does spectral broadening make it harder to measure drift rate?
Yeah, so if you have a signal that is like a 1 or like a couple of hertz wide, that allows you to search for drift rate, you need to observe a little bit longer so that your signal is actually drifted further away to the next frequency bin so that you can search it. So in that case, it makes it difficult. So you just need to observe for a little longer. And for given observing length, your signal, the amount of drift rate you will be able to search, like the minimum drift you will be able to search will be limited to the spectrally broadened signal. Higher ones is kind of obviously not constrained by this, but the lowest drift rate that you can search will be constrained by the spectral broadening.
All right, we got a fun question from Nick. You referred to the Great Silence. Is it possible that one of the challenges of SETI is that the bulk of investigations rely on EDI wanting to intentionally communicate with us? And should SETI prioritize technosignatures that do not rely on this assumption?
Yes, I absolutely agree with that, Nick. And that's what I was kind of saying earlier. We don't necessarily need. I mean, then again, the question comes like if I say that we need to search for signal that are leak emission from the ETI's activity, as sort of Mike was saying in the morning. How far we can extrapolate our own technology to kind of say that the signal that we will detect as a leakage radiation will be something that we can actually identify. That has to be sort of some kind of technology overlap between us and ETI. Now, ETI may have been so far ahead advanced than us that their leaked emission or their leaked transmission would be something that we may not be able to identify. It may just look like sort of pure noise to us. In that case, it will be challenging. But if there is indeed some energy, so the way we are currently searching, we're looking for example, things like cyclostationary signal. So if there is a repeated pattern, for example, if there is any energy in a certain frequency in time space, you will be at least be able to identify those. Even if you are not able to understand what exactly that signal is there any modulations or not, you may not be able to decipher, demodulate, but at least what you will be able to say is that there is some coherent signal there which appears to be artificially generated, and it's coming from sky. If I say that, I think that's kind of a good deal for SETI as well. We don't necessarily need to decipher, demodulate, or understand what exactly it means. So yeah, that's what I'm kind of meant on that.